Hello, we are Team 20. This is Reed Backus speaking, and I'm here with Brendan Mowers, Nolan Bainbridge, and Luke Greiser. We are presenting our interim presentation of the 5-claw gripper. So first, I'm going to go over a little bit of a product description of what a gripper is. So there are about 435,000 new units of industrial robots this past year. And by 2023, there's going to be over 4.4 million units in total worldwide. And a gripper is a type of end of arm tool that is used to be attached to some industrial robots. They're used to move and assemble parts, so they pretty much can grip anything with varying shapes. And the 5-claw gripper that we chose is an electromechanical example of one that can grip objects concentrically. Different grips can be swapped onto the claws to manipulate different types of parts. And the carpal extenders on our product, which will be shown on the next slide, move linearly to actuate the claws. Shown here to the left is the total assembly of our 5-claw gripper, and shown to the right is an exploded view. This is an exploded view of one claw for simplicity, but each claw is identical to each other. There are 11 unique components, excluding fasteners. And again, the carpal extender moves linearly up and down to move the rest of the claw, and that can kind of be seen from the exploded view. The primary and secondary customers for this type of gripper would be both from automated manufacturing applications. Grippers are needed in many different types of industries, basically for the same general purpose, and that is to move and assemble components. Gripper claws, as I mentioned before, can be modified for different applications in different industries. The primary and secondary customer bases would be the two biggest segments of the global articulated robotics market, and that is the automotive and electronics industry, respectively. And once again, the tips of these grippers can be changed to be more robust, bigger, smaller for different types of components. I just want to note that these production volume estimates are they're estimates and they're for educational purposes only for this project. Finally, I'm going to go over the functional analysis. The primary goal of the grippers is to manipulate objects. From there, you need to first hold on to an object and then release an object. Holding on to an object requires you to add force to the object through the claws and contact the claws against the object, of course. To release the object, you need to release force and then also move the claws enough to have clearance between your object and your claws to be able to drop it. To assure dependability, you need to maintain force, possibly by locking a mechanism. And to enhance the product, you can vary the contact and adapt the amount of force you are putting into the claws to hold different objects. And that involves also changing the geometry.
Next is our assembly sequence analysis. The main difference between the two assemblies is that the order of the claw assembly and the extender assembly are switched. Sequence 2 scores higher due to its ease of assembly in parallel and ease of testing subassemblies. Here is our functional component mapping table. Each part of the assembly was matched to each terminal subfunction, verifying our fast diagram.
Shown here is the bill of materials for our product. Part numbers and names can be found on the leftmost side and correspond to the exploded view from earlier in this presentation. Materials were selected based on part function, and subsequent manufacturing processes were selected based on material, batch size, part size, and approximate tolerance. Assembly process was based on our best assembly sequence, and costs were calculated using a combination of custompartnet, custompartnet.com, and hubs. And then on the rightmost end of that table, there's a breakdown for the quad chart for DfMA, discussed in lecture, which highlights parts for potential redesign and elimination. In terms of verifying this total cost, the $267 can be compared to a real world product, which is seen on the left there. The cost of $2,230 was broken down to 50% of that cost in order to account for price markup. And compared to that cost from earlier, the difference really is due to the choice of injection molding the claws out of the HDPD or HDPE for price trade-off. There's potential wear here, but easy replacement. And then the tables here break down the product family design in terms of functional differentiation and component commonality. Different functions are broken into things that were the same for both customer groups and different, and then allowed us to map this over to component commonality in terms of what parts map back to those functions.
And here you can see the two different final products based on different user groups. And it'll be broken down more on the next slide, but you can see based on the carpal knuckle. With the dovetail design, it'll allow for multiple different claw designs based on the user group and what functionality they need out of the product. So here you can see a couple of the different designs. So the primary user group is an automotive component grabbing. So you can see it's just an overall wider and more robust grabbing mechanism, as well as a staggered profiled gripper. Whereas for electronics with more delicate components, you need more dexterity for smaller and more breakable components. So it's got a more pointed tip and a smoother and softer rubber design for the gripper. And here you can see our assembly sequence diagrams, starting off with the assembly sequence discussed previously. We saw that there was some room for improvement using delayed differentiation, and you can see the modified assembly sequence below based on that to make a more streamlined process. Thank you. That is the end of our presentation.